So now we figured out our relationship between our k's, and now we want to find our relationship between our omega, our angular frequencies. So we have that the original frequency, when it's stationary, is just the square root of k over small m, since small m is the one that's oscillating, while large M is the box that is being stationary. And omega 1 is just equal to the square root of k1. And for k1 in this case, we have its large M, that is the one that is oscillating. So we have this, and when we plug in what we know for k1 here, we find that it's simply equal to k over the square root of large M times large M plus small m over small m, which we can simplify since we know that k over m, the square root of k over m, is just omega. This is just equal to omega times large M plus small m over large M. Now similarly, we have omega 2, which is the square root of k2 over small m, since in this case small m is the one that is going to be oscillating. We can replace k2 with k, we have divided by m, large M plus small m, all over large M. And once again, we recognize this to be omega, so we have omega times the square root of large M plus small m over large M. What we find about these things is that in reality, omega 1 and omega 2 are the same, which is to say that the angular frequency of oscillation for both the mass hanging from the spring and the box within, their angular frequencies are the same. Now when we compare omega 1 and omega 2, which is both omega large M plus m over m to omega, we find that this ratio, namely large M plus small m over large M, since we know that both masses will always be positive, we know that this expression will be greater than 1, and thus we find that the new frequency, omega prime, which is basically omega 1 and omega 2, will actually be larger than our original frequency. So we find that the frequency will increase upon dropping our box to start falling freely under gravity.